why can this circuit board bend thousands of times, while a normal PCB shatters? Look inside almost every modern smartphone, wearable, or folding device, and you'll find them. Flexible printed circuit boards. They snake through impossibly tight spaces, survive constant motion, and still carry high-speed signals. But how are these circuits actually made? And why does their manufacturing look so different from the rigid boards we already know? The answer is not more steps. It's a series of deliberate engineering solutions to one core problem. How do you keep copper traces electrically perfect while the entire board must remain mechanically alive? Let's go inside the factory. Flexible PCB manufacturing actually begins on familiar ground. It starts with a copper-clad laminate, much like a standard PCB, except the rigid FR4 core is replaced by a thin, flexible polyimide film. From there, the board goes through the same fundamental steps. Holes are created, copper is built up, and precise circuit patterns are etched into place. Electrically, the foundation is identical. The conductive pathways are born the exact same way, but mechanically, that's where everything changes. Take the first hurdle, protecting copper traces that are born to move. Conventional solder mask protects static boards well, but repeated flexing eventually creates cracks and delamination. The solution is coverlay, a polyimide film coated with adhesive. Before being permanently laminated, precise openings are created wherever solder pads, connector contacts, or test points need to remain exposed. The coverlay is then carefully aligned, temporarily secured in position. And finally, laminated under heat and pressure, forming a flexible, protective layer that bends together with the copper traces. Yet, flexibility isn't always a virtue. In fact, pure flexibility can be a liability. A connector must be inserted without crushing. A chip must be soldered without the pad lifting. A battery contact needs consistent pressure. So manufacturers selectively bond stiffeners, polyimide, FR4, or stainless steel, only in the zones that require rigidity. The rest of the board stays fully flexible. This hybrid behavior is impossible with a standard rigid PCB. Stiffener bonding exists to give mechanical strength precisely where physics demands it, without sacrificing the bendable regions. Then comes the spatial puzzle. These circuits don't just sit flat, they must conform to complex, three-dimensional spaces. Mechanical routing that works on thick, rigid boards can tear or distort thin, flexible laminates. Complex outlines, dynamic bend zones, and tiny retention features demand far higher precision. Laser cutting and precision die cutting are selected according to the required geometry, material, and production volume. They create clean edges, exact bend lines, and intricate geometries while keeping residual stress minimal. Here is what most people never realize. Rigid PCB manufacturing is relatively standardized. Flexible PCB manufacturing is radically customized. A smartphone display flex may need ultra-thin materials, controlled impedance, and EMI shielding film. A wearable may add pressure-sensitive adhesive for assembly, while an LED light strip focuses on thermal paths and length. Optional processes, shielding films, selective tapes, metal reinforcement, thermal interface layers, appear only when the product physics require them. Each board is an engineered response to a unique combination of bend life, space, signal integrity, and environment. Flexible PCB manufacturing shares its electrical foundation with rigid boards. But every distinctive process exists to solve a mechanical or reliability problem that rigid manufacturing never faces. The philosophy is constant balance, flexibility against strength, thinness against durability, electrical precision against dynamic motion. That is what makes flexible PCB manufacturing fundamentally different. If you enjoyed the journey, hit the like button, share it with others, and drop a comment telling me which production process you'd like to explore next. Catch you in the next video.